Legend has it that on a certain day of 1666, Newton discovered the law of gravitation, a law that applies to all objects in this universe, when he saw an apple falling from a tree.
This story might not be true, but it is a fact that an apple tree was planted in the garden of the house where Newton once lived.
In fact, scientists before Galileo and Newton generally believed that the sky, where celestial bodies such as the moon, the sun, and various planets are, and the earth in which we live in, were not at the same level of existence. They thought that the laws of physics that were used to explain the relationship between objects on earth were not applicable to celestial bodies in the sky. For example, objects on Earth would undergo various accelerated motions where force is exerted on them, but celestial bodies in the sky would only have circular motions.
Why are the motions of the objects in the sky different from those on Earth? For example, why do apples fall from the tree, but why doesn't the moon fall onto the Earth? The only possible answer is that those scientists' theory was wrong.
This is also what Newton thought. After much thought and rigorous research, Newton eventually overthrew their theory and proposed the law of gravitation. That is, there is a force of attraction between all objects. Such a force applied to all objects, including the celestial bodies in the sky.
In fact, scientists before Newton had already discovered and put forward the concept of gravitation, but only Newton employed mathematical principles to prove that gravitation exists in all objects. For example, the nature of the force that causes an apple to fall is the same as the force that makes the moon revolve around the Earth. Moreover, this force is universally applied to all physical bodies having mass and acts on all objects of the universe. Why can I hardly experience any gravitational force between objects?
There are two apples on the table, but there doesn't seem to be any force of attraction between them. According to Newton's law of gravitation, there is indeed a gravitational force between the two apples. However, the force is so weak that it has been cancelled out by the friction between the apple and the table. That's why the apples aren't pulled towards each other.
As the gravitational force between the objects we encounter in our daily life is really weak, we can hardly feel its presence.
In 1687, Newton explained the law of universal gravitation in his book, Mathematic Principle of Natural Philosophy. Every point mass attracts every single other mass by a force pointing along the line intersecting both points. The force is proportional to the product of the two masses and inversely proportional to the square of the distance between them. Whoa, that seems really hard to understand, doesn't it? If the spatial extent of the object is limited, we can assume that all the mass is concentrated at the center of the object. It is called the point mass. Gravitational force refers to the attraction between objects. It is kind of action and reaction forces. In simple terms, the gravitational force acting on two-point masses is directly proportional to the product of the masses, and is inversely proportional to the square of the distance between them.
Newton believed that when the distance between two objects is doubled, the gravitational force between them would be reduced to 1/4. In other words, gravitational force is inversely proportional to the square of the distance. It is known as the inverse square law. Why is gravitational force inversely proportional to the square of the distance? Imagine there is a point light source. The amount of light from this source that passes through the base of two square pyramids labeled A and B, respectively, is equal. As the distance from B to the light source is 2 times the distance of A from the source, the area of B will be 2 times 2 of A's area, which is 4 times. Therefore, the intensity of light passing through B, namely the amount of light divided by the area, would be 1/4 of A. This shows that the intensity of light emitted from the light source is inversely proportional to the square of the distance. If this line of thinking is applied to the case of gravitation, we will be able to understand the inverse square law.
But there is still one puzzle to be solved. As the moon is also subject to the gravitational attraction of the Earth, why doesn't it fall onto the Earth like an apple? Why?
This pocket watch can give me the answer. When I twirl the pocket watch around with a chain, the pocket watch actually rotates in circular motion. When the watch is in circular motion, a force must be acting on the watch towards my hand, that is the center of the circle. If the chain breaks, the watch will immediately be thrown outwards in the direction of motion at that moment because of inertia. To be in circular motion, a force must be acting on the watch towards the center of the circle. In circular motion, the force that acts towards the center is called centripetal force. Let us assume that the moon revolves around the Earth in circular orbit at constant speed. The centripetal force required by the moon is provided by the gravitational force of the Earth on the moon. As this centripetal force is always perpendicular to the motion of the moon, it does no work on the moon. As a result, the gravitational force on the moon always keeps changing the direction of motion on the moon. The velocity changes, but the speed remains constant. Therefore, the moon keeps revolving around the Earth at this speed without falling down. But it's not completely wrong to say that the moon is gradually falling down onto the Earth.
Because of gravity, the path of the moon is continuously changing. When the circular path of the motion of the moon is compared to the straight outward path of the moon if gravity is absent, then the difference will show that the moon is continuously falling down. However, due to the circular path of the moon always keeps the same distance from the Earth. Therefore, it can be said that the moon will never fall down onto the Earth.
Newton stated that gravitational force is inversely proportional to the square of the distance. How did Newton come to this conclusion? There is a story behind this.
In the same period of Galileo, before Newton was born, there was a Danish astronomer called Tycho Brahe. Brahe recorded the positions of the planets in the sky with the help of his innovative astronomical instruments. At that time, he had already discovered that many of the planetary positions recorded in books were not accurate. When he died, he left behind a huge amount of information on the observation of planetary motions. Brahe's assistant, the German astronomer Kepler, continued the research of Brahe and analyzed the information Brahe collected.
Astronomers in the past, whether Ptolemy or Copernicus, all believed that the planets in the sky moved in circular motions. Kepler thought the same initially, but after examining the information of the motions of Mars obtained by Brahe as well as making calculations based on the assumptions of circular orbits, he discovered discrepancies. No matter how Kepler did his calculations, he found that the trajectory of Mars could not be confined to circular orbit. But he never queried the data collected by Brahe and managed to find clues from different types of graphs. He found that there were more complicated conics than circles. He discovered that the orbit of Mars was an ellipse rather than a circle. This finding was later known as Kepler's first law.
Around 1605, based on Brahe's data on the position of planets, Kepler discovered that the motions of planets followed three simple laws. He then worked very hard to record his discoveries in an article published in the scientific journal Astronomia Nova. What are those three laws? What is the relationship between those laws and Newton's law of gravitation? Let's look at the three laws first.
Kepler's first law states that the orbit of a planet is an ellipse, with the Sun at one of the two foci of the ellipse. Let's continue. Kepler's second law states that a line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. Finally, Kepler's third law states that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. These three so-called simple laws are actually not simple at all. Concerning the first law, in the past, Kepler only considered the circular orbit, and so the observations did not match the data. What then is an ellipse?
An ellipse is a flattened circle with no center but two foci. The sum of the distance between any point on the ellipse and two foci is always constant.
We pin two pins on a piece of paper and tie a piece of inextensible string to the pins. Then loop the piece of string around a pencil so that the pencil forms a triangle with the two pins. Move the pen while keeping the string loop taut and an ellipse is traced. But there is still a riddle. That planetary orbits are elliptical seems to be a simple fact. Why had it taken several hundred years before Kepler unraveled it?
First of all, we need to understand that while there is one center in a circle, there are two foci in an ellipse. The distance between the two foci determines how round or flat the ellipse is. The further apart the two foci are, the flatter the ellipse. In other words, the eccentricity of the ellipse is greater. The closer the two foci are, the rounder the ellipse. Eventually, the ellipse would become a circle when the two foci overlap. The eccentricity then becomes zero. The circle is actually a special form of an ellipse.
In the solar system, the eccentricity of planets revolving around the Sun is very small. That's why past astronomers treated planetary orbits as circular. This led to the discrepancies between the theoretically predicted positions of planets and their observed positions. Thanks to Brahe's years of precise observations and Kepler's meticulous calculations, the riddle was finally resolved. The fact that Kepler had chosen to study Mars was also key to the successful discovery because Mars has the most prominent elliptical orbit in the solar system. Kepler's laws posed great challenges to Aristotle and Ptolemy's schools of thoughts in the areas of astronomy and physics. For example, he argued in his first law that the Earth is constantly moving forward and that planetary orbit is elliptical and not circular. With regard to the second law, as planets follow an elliptical orbit, their distance from the Sun constantly changes. But since Kepler discovered that the line between a planet and the Sun sweeps out equal areas during intervals of time, it means that planets sometimes move faster and sometimes slower when they orbit the Sun. It implies that orbital speed is not constant. These arguments considerably shook the worlds of astronomy and physics of the time.
Kepler derived his laws from his experiences in astronomical observations. Although Kepler tried hard to find out why these laws could be established, for example, why planets would sometimes move faster and at other times slower when orbiting the Sun, he was never able to draw a correct conclusion.
Newton, however, was different from the scientists before him. While the past scientists relied on observations and data, Newton believed it was the most important to identify the relationship between interacting objects. From his very own Newtonian mechanics and law of gravitation, Newton deduced Kepler's third law mathematically. Kepler's third law is also an important basis for Newton's law of gravitation.